Okay, so today is Wednesday, the 20th, and we're doing arcsin and arccosine. We're going to remind you about the domain and range of those functions. We're going to remind you about the arithmetic of those functions. We're going to remind you about the algebra of those functions, and then we're going to figure out some derivatives. Yay! All right, so kindly consider the following. Where is it? There it is. What if y is arcsin? What the heck does that mean?
Just the inverse of sine.
The inverse of sine, right? The functional inverse, right? What does that look like?
Just a reflection of sine over the line
Y equals x, exactly. Well, let's see. What does that look like on Hal? Let's go to Hal for 1 second. And what I'm going to do is, no, I need to go over here. Yeah, I'm going to go to, why does this keep on coming on? Go away. Let's go to parametric mode. And in y equals, I'm going to graph, whoops, what happened? Mode, parametric mode, enter, enter. Very interesting. That was weird. Okay, I'm going to clear that, going to clear that, going to clear that, going to clear that. Okay, what if I graph sine this way? X is t, and y is sine of t. Okay, wait, hang on, hang on. Actually, we have an arcsin here, don't we? Well, I'm going to show you this for a reason, all right? I could have graphed arcsin otherwise. Now, what I really want to do is graph the inverse function, which means all the x's and all the y's are swapped. So here, I'm going to graph x, instead of x, I'm going to graph the y values, yt1 of t. And the associated x values, xt1 of t. It's a weird function name, but there it is. And if we graph that, let's see, zoom, I don't know, trig, what does it look like? There's your sine, and there's your arcsine. Okay? Now it depends. Are we going to define the, if we take the piece of the sine wave from 0 to imagine that's 2 pi, wait, trace this. Is that pi over 2? Yeah. So that's pi, and that's 3 pi over 2, and that's 2 pi. Okay, yeah. So if we restrict the domain of the sine from 0 to 2 pi, then that's the arcsine. But that's not the traditional definition of arcsine. The traditional definition of arcsine is, notice I restricted my t values, my angles I'm plugging into sine from 0 to 2 pi. What if you do it this way? Let's see. How about negative pi to pi instead? What does that look like? So now this piece of the sine wave is what we're talking about, right? And then here's the arcsine. What's the problem with this? It's not a function. So I can't do that either. What if I do this? What if I go from negative, not pi, but pi over 2 to positive pi over 2? And that's a more standard definition. What you got to do is take a piece of the sine before you reflect it across the line y equals x, like Daniel said, and make sure that that piece of the sine, when reflected, is still a function. So I can only take this much, and I could take it just about anywhere, but this is the standard definition of arcsine. So if we regraph, no, it is inclusive. It's okay. Yeah. All right. So if the domain, all right, you know, it's hard to see which is which. I'm going to do this. Diamond F1 is F6. I'm going to change one of these to thick. How about the inverse? I'm going to make this a thick line so it's easy to see it. What happened to my diamond F6 style, right? And let's make it thick. Make it stand out. Okay. Graph. So here's sine, and here's arcsine. Okay. So the sine, what's the domain? Negative pi over 2 to pi over 2. That tells me the range of the inverse function. What is it? Right, negative pi over 2 to pi over 2. What's the range of sine? Negative 1 to 1. So what's the domain of arcsine? Negative 1 to 1. Which is hard to see here because this tick mark, you think it's negative 1, but it isn't. It's negative pi over 2 in zoom trig. If you do this in zoom 4, it might be easier to see. There's the sine and there's the arcsin. So the arcsin goes from x is negative 1 to x is positive 1, and from y is negative pi over 2 to y is positive pi over 2. That's the arcsin, okay? What does the arc cosine look like? Well, change this up. Make this a cosine instead. We'll enter. Okay, so second cosine of t. All right, now let's graph that. So there's a piece of the cosine, but what about the arc cosine? Not a function, right? Doesn't pass vertical line test almost anywhere. Epic fail, exactly. So you know what we do is we redefine the domain of the cosine from 0 to 2 pi. That's the standard definition. Again, you can pick any slice of cosine that will reflect to a function, but traditionally we use 0 to 2 pi for arc cosine, so let's put in 0 here and 2 pi here. Whoops, I lost the 2. Boom. And this, by the way, this is pi over 24, so it's easy to trace values like pi over 3, pi over 4, pi over 6. So, you know, that's the reference angles. And graph that. So here's a piece of the cosine. No, wrong. No, right, that's right, yeah. This is 2 pi. Okay. So I'm in zoom 4. It's hard to see what I'm doing here. Zoom trig would look like this. Okay, so the domain of cosine is 0 to 2 pi. The range of arc cosine is 0 to 2 pi. The range of cosine is negative 1 to 1. The domain of arc cosine is negative 1 to 1. Remember that inverse functions and their associated functions, they're just swapping the domain and the range. It does, yeah.
The domain repeats itself.
Well, the domain of one is the range of the other.
Yeah, no, I know that. But I'm saying the domain of the...
Well, because it's periodic, that's why we don't have a function if we're not careful.
Yeah, so...
Ethan, you're saying?
Standard domain?
That's standard, yeah. What doesn't pass the vertical line test? It does, though. It's this thick piece here. Oh, is 2 pi too much? Wait, hang on. Let's go. Let's see the range from, let's say, from 0 to.
Well, not 0, because then you wouldn't be able to see the other. So make it 0, make it like -2.
Well, I made the domain of cosine 0 to 2 pi, so the range of arc cosine should be 0 to 2 pi also. So let's see the whole thing. Is 0 to 2 pi too much? Maybe it's, yeah, that's a problem. It's 0, yeah, it's 0 to pi. Sorry, I misspoke myself. 0 to pi. 0 to pi. Thank you. Good call. How about we do a zoom 4 on that? Okay, so just from 0 to pi, and then the range is from 0 to pi. That's good, yeah, good. That's it. Okay. All right, so now that you know what the thick graph, that's the graph we're talking about. Okay, that's the thing we want to figure out derivatives, all kinds of fun stuff about. So let's do so. Let's see if we remember some stuff. What if I asked you for the arc cosine of rad 3 over 2? What is that? I call this the arithmetic of arc cosine. Just plugging in numbers, getting out numbers. Now, it's called arc cosine because it's an arc of the unit circle. It's a piece of the unit circle. It's an angle is what you get. If you plug in an angle here, you get a sine. Wait, I'm sorry. If you plug in an angle into the sine, you get a sine value, right? But what you do with the arc sine is you plug in a sine value, and you get the angle that goes with it. That's what arc means, the angle whose sine is. Okay? So I'm asking you for the angle whose cosine is rad 3 over 2, and what do you say? Shelley? 30? In other words, pi over 6? Is that so? Remember a right triangle with 60 degrees or pi over 3, 30 degrees or pi over 6. This is 1, this is 1/2, this is rad 3 over 2. So is the cosine of pi over 6 rad 3 over 2? Yeah, adjacent over hypotenuse. You're right. But let's keep to radian mode. We're talking about radians, right? Okay, so it's just a little arithmetic, just plugging in numbers, getting out numbers. What's the arcsine of 1/2? The angle whose sine is 1/2. What do you say?
1/2.
It has to be an angle. Give me radians.
60.
It's also pi over 6. Look. Remember, sokato, the sine of pi over 6, 30 degrees, is the opposite over the hypotenuse. It's 1/2 over 1. The angle whose sine is 1/2 is 30 degrees. Okay. What about the angle whose cosine is negative 1/2? Well, where's the cosine negative? Remember, we restricted...
35?
Is it 5 pi over 6?
No, is that 135? No.
No, that's... You have 3 pi over 4. You're saying 3 pi over 4. He's saying 5 pi over 6. Well, remember, we restricted the domain of the cosine from 0 to pi. So the answers we're going to get, the range of the arc cosine is 0 to pi. First quadrant to second quadrant, where's the cosine negative? Second quadrant. Now forget about the quadrants. What angle has a positive 1/2? Isn't the cosine of, cosine is 60, 1/2, the adjacent over the hypotenuse, right? So in the first quadrant, you get pi over 3. In the second quadrant, you get pi minus pi over 3, which is 2 pi over 3. 120 degrees? Okay, so Patrick was thinking the reference angle was 45 degrees at pi over 4. Ethan was thinking the reference angle was 30 degrees at pi over 6. The reference angle is pi over 3, 60 degrees.
Oh, we were both wrong.
Oh boy, now you have something in common. Okay, what's the angle whose sine is negative rad 3 over 2? Now remember, we restricted the sine from, what was it, negative pi over 2 to pi over 2. So I need angles in the first or fourth quadrants. Where's the sine negative? First or fourth quadrant? Fourth, okay. Now forget the SIGN of the SINE. What reference angle has a sine of rad 3 over 2? Pi over 6, right? The opposite of the hypotenuse, right? So if pi over 6 is the reference angle in the first quadrant, but I want to be in the fourth quadrant.
You got 3 pi minus it from 2 pi.
Remember, we restricted the domain of cosine from 0 to pi, so that's the answers we're going to get from the arc cosine. We restricted the domain of sine from negative pi over 2 to pi over 2. Okay? So that's the answers you're going to get here. No, that's it. We're not allowing numbers outside of this range.
Out of the 180.
Right. Well, this would technically be negative 90 to positive 90. 0 to positive 180, right? All right, so that's a little bit of arithmetic that you should know from somewhere in your vast store of knowledge. Here's some algebra. What if I want to solve this equation for alpha? The sine of alpha is rad 3 over 2. How do you solve this? How do you get alpha alone? How do you get rid of sine?
You have to get rid of the sine.
How?
Inverse.
The inverse sine. That's the whole point of having inverse functions. They cancel stuff, right? Like e to the cancels ln. They're inverse functions too. Okay, so arc sine both sides, and you get alpha is the angle whose sine is rad 3 over 2. And didn't we say that was? 3. 60 degrees. Good. All right. Good, good, good. All right, here's another algebraic question. I should just move this down a little bit. What is the secant? Say that you have this in an equation, you want to simplify it, okay? What is the secant of the angle whose tangent is x over 3? Now, this is not a numeric result. This is going to be an algebraic simplification. You're going to get something in terms of x. Notice, a secant wants an angle. Arctan of stuff is an angle. Arctans give you angles, right? Okay. So what angle, what's the angle whose tangent is x over 3? Well, you have to construct it. Here's a right triangle. sort of. Say this is the angle in question. Can you construct this triangle such that this angle has a tangent of x over 3? What does SOHCAHTOA say about tangent? Opposite over adjacent, x over 3. But I want the secant. The secant is 1 over the cosine. How do you get the cosine of theta? The adjacent over the hypotenuse. So I need the hypotenuse. But Pythagoras says x squared plus 9 square root is the hypotenuse. So what is this? It's 3 over that. This is the algebra of arcsine, arccosine, arctangent. All right, let's do a little calculus. Let's do some volume stuff. How about this? Ready? Can I move to the next page? All righty, let's do so. How about, okay, let's say I give you the following graph. Let's make a little graph. Let me think about this. 3 over 2. 1 secant. Okay. I'm going to give you this graph. It's going to be the arc secant from x equals 1 to x equals 2. How do I know what the arc secant looks like? Did we ever graph that? We graphed the arcsine, the arccosine. What's the arc secant? The inverse function of, no, not cosine, secant, which is, what's secant? 1 over cosine. So if I go back to Hal and ask Hal to graph the, go away, the inverse function for arc, let's see, I want the arc secant, so the inverse function of secant, I have to change this to what? 1 divided by cosine. I don't know about the domain, but let's see what this looks like.
Wow.
Yeah, that's not a good domain. Let's see, what's a good domain? Let's see, what's my domain right now? 0 to, how about this? Let me try negative pi over 2 and positive pi over 2. I think that's a good restriction on the secant's domain, so we can see what the arc secant looks like. There's a secant, there's the arc secant. Okay? So I'm talking about this piece of the curve, from x equals 1 to x equals 2. Okay? Oh, is that right? Wait, hang on. Zoom 4. Yeah, it's from 1 to 2, that's right. So that's the graph I was giving you. Okay? I want the volume generated when I take this thing and revolve it around the y-axis. I want to take this thing and revolve it around the y-axis. How are you going to do it?
So you have to do,
If you do vertical strips, it's disc washer shell. Which? Dun, 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 dun. If I take a vertical strip around the y-axis, disc washer shell. That's shell. If I do a horizontal strip around the y-axis, it's disc washer shell. Washer. You know what? I think that might be easier. Let's see that. What's the thickness of my Riemann rectangle? dy. By the way, secant is 1 over the cosine. The angle whose secant is 1 is 0. That's why it goes through 1, 0, right? The angle whose secant is 2 is the angle whose cosine is a half. Is pi over 3, right? So you know the range of this piece of the curve. You know the domain of this piece of the curve, right? So why do I need to know this? I need the y values because I'm going to do this in dy. All right, so the thickness of the rectangle is dy. What's the height of the rectangle? From the y-axis. 2. That's the top minus the bottom. Well, it's this as a function in y. How do you get this x alone? Secant both sides. So if I secant both sides, I get x is secant y, right? Okay, so I'm going to take big disk minus little disk. Remember big disk? Pi big R squared dy minus pi little r squared dy. Okay, so the volume about the y-axis is pi big R. What's big R squared? I want the integral from 0 to pi over 3 of big R squared, which is 4, right? Minus little r squared, secant squared of y, times the thickness of each of the disks, dy. Can you do this analytically?
Yeah.
The antiderivative of 4 dy is just y. All right, so let's write that. Let's say I get pi times y. And the antiderivative of secant squared y dy is 10. And we want to evaluate this from 0 to pi over 3. And so what do you get? Well, let's see, pi times, plug in pi over 3 minus a tan of pi over 3 minus plug in 0. 0 minus a tan is 0. Well, the tangent of 0 is 0, so this all drops out, right? The tangent of pi over 3 is a sine of pi over 3 over the cosine of pi over 3. The sine of pi over 3, remember, was rad 3 over 2. The cosine of pi over 3 is 1/2. What rad 3 over 2 divided by 1/2 is just rad 3. So you get pi times pi over 3 minus rad 3. What happened?
How do you get 4 minus secant squared of y minus tan?
Well, because the antiderivative of 4 dy is, oh, well, I lost the 4, I'm sorry. Is that what you're talking about?
Yeah.
Whoops, sorry, there's still a 4 here, so there's still a 4 here, and there's still a 4 here. Whoops, do as I say, not as I do. Did I mess up something else? I think that's good. Okay? Sorry, I lost the 4. Yeah, the 4's there, the 4's there. Okay, good. Okay, so that's an integral involving things to do with arcsine, arcsecant, or arcsine or cosine, whatever, it's all the same. What about derivatives now? Can you tell me the derivative of the arcsine? Let's talk about that. Moving ahead. Okay, let's say that y is the arcsine. Yeah. Can you tell me the derivative? dy dx, let's say. Think how we did it with ln. Ethan, any ideas?
You could just take the sine of both sides.
Right. If I take the sine of both sides, what do I get? Sine of y equals x. And we can differentiate this implicitly with respect to x. Y is a function in x, so you're going to get dy dx from the chain rule. That's what I want, right? So what's the derivative of sine of u, or sine of y? Cosine y times dy dx, times the derivative of the inside. This is not just x. This is some function in x. You've got to do the chain rule. Equals, derivative of x is 1. So how do I get dy dx alone? So dy dx is 1 over cosine y. Yeah, but can I put this back in terms of x? Because I know who y is. Y is the angle whose sine is x. Construct the right triangle.
1 cosine y dx.
Do you know an angle? Can you construct a triangle such that there's an angle? This is y. I could call it y, I guess. Let me call it y. Y is the angle in some right triangle that you can construct such that its sine is x. Now remember, SOHCAHTOA says what about sine? Opposite over hypotenuse. Doesn't that angle have a sine of x over 1 is x? But I want the cosine. How do you get cosine of the angle? Adjacent over hypotenuse. So I need the adjacent. How do you get this guy?
I know. Wait, stop. Oh.
Dang it. If I call it a squared plus x squared equals 1, right?
Yeah, that's what I was thinking.
I want to get a, so a squared equals 1 minus x squared. So a is the square root of that. I can't write. What the hell? A squared is 1 minus x squared. So a is the square root of that. So what's the cosine of y? A over 1. But A is a square root. Yep. So y prime, among friends who are saying dy dx, is 1 over rad 1 minus x squared. Okay. Can you do the same thing for the arc cosine? So, by the way, that gives you two rules. The derivative of the arcsine is this. The antiderivative of weird stuff like that is arcsine. Okay? So you can go back and forth, right? So the derivative of this is this, the antiderivative of this is that. So this is, again, some kind of a quotient rule for integrals. Right? We're going to talk about next week sort of a product rule for integrals. There is one product rule for integrals, sort of. There isn't one product rule for quotients. I'm sorry, one quotient rule for integrals. There's a whole bunch of different ones. Some involve ln, some involve arcsine, arccosine, arctangent. It's weird. Some involve something completely different. You're ready. All right, so you try it. Y is arccosine. Can you get its derivative? I want the derivative of the arc cosine. I did the derivative of arcsine. Can you get the derivative of arc cosine the same way? Sure you can. All right, here we go. Where am I? Okay, so let's say y is arc cosine. What's dy dx? I'll call it y prime, just for fun. Okay, so what do you think you do first? Take the cosine of both sides, right? So what do you write? Cos y is x. Okay. And now what? Take the derivative of both sides. So what do you get? Negative the sine of y, dy dx equals 1. So dy dx alone is 1 over negative sine y. Can you rewrite that in terms of x? Sure you can. Construct a right triangle. Now remember, y is the angle whose cosine is x. So here's y. How do you make this construct give y a cosine of x? Adjacent is? Hypotenuse is? 1. Remember, it's adjacent over hypotenuse has to be x, because that's the cosine. But wait, I want the sine, so don't I need the opposite over the hypotenuse, right? What's this? How do you get the sine? Again, if you call this b, you got b squared plus x squared equals 1 squared, so b squared is 1 minus x squared, so b is the square root of that. So I want negative the square root of that. Okay, so let's write that. Dy dx is the opposite of 1 over rad 1 minus x squared. I'll put the negative on top, doesn't matter. All right, you know what? I got to save this. Hang on. Because it went to